I'm going to take a look at rotational inertia or moment of inertia. When we talk about inertial mass, we're talking about m, the translational inertia, which is an object's ability to resist linear acceleration. So if, let's say your car runs out of gas, if you're driving a semi and you need to push it off the road, it's going to be really hard for you to get it moving because it's got a lot of mass. But if you have a smart car and you need to push it off the road, that's going to be a lot easier because it has a lot less mass. So the equivalent in rotation is rotational inertia or moment of inertia. And that's an object's ability to resist rotating. So the rotational acceleration. The variable that we use for that is I. I don't know why. It's not even Greek. I'm not sure. And the units of that, instead of being kilograms, are kilogram meters squared. So objects with most of their mass near their axis of rotation end up with a smaller I, and objects with more mass further from their axis of rotation have a bigger I. So it's harder to rotate if more of your mass is spread apart. So the equation that you get, unfortunately, only APC gets an equation for this. I really don't understand how the AP folks decide what they stick on there. Is the integral of r squared dm, which should look a little familiar to those of you in APC because we talked about that with changing mass before, and that was why. We're going to get to that next week. But the part that I want you to focus on today is that it's the sum of mr squared. For AP1, they don't give you this equation, but you need to know that part of it, so that I is equal to the sum of mr squared. So your I is going to depend on where the axis of rotation is, so how far away you are, that's the R, and also how much mass you have. For APC, if you're doing point masses, you're going to use the sum, this part of the equation, rather than the integral. We'll use the integral part next week. So let's go through a couple of examples. First one, we have two bowling balls that are joined by a meter-long rod that doesn't have any mass to it. And we want to know what is the rotational inertia when it's rotated about the center of the rod. So our equation is I is equal to the sum of mr squared. We have two objects, so we're going to have m1 r1 squared plus m2 r2 squared. So the 5 kilograms is the mass of each one, and our r is the distance to the axis of rotation. Since it's a meter between the two objects, the distance to the axis is going to be 0.5 meters for both of them. So we plug it in, we end up with 2.5 kilogram meters squared. Another example, now we're going to do the same two bowling balls, but instead of rotating it about the center, we're going to rotate it about one end. So the axis of rotation is changed. We have the same equation, and when we plug stuff in, we now have 5 kilograms times 1 meter squared plus 5 kilograms times 0 meters squared, because that second bowling ball is right at the axis of rotation. So when we plug that in, we end up with an I value that's twice what the other one was. This is a higher I value. It's going to be harder to rotate this object than it is the last object, which you can think about, if you have two heavy textbooks and want to just try it out. If you pick up both textbooks, put them in close to you and spin around. It's a lot easier than if you take the two big heavy textbooks, hold them at arm's length and try to spin around. Try this. So we have 6 brass and aluminum spheres that are connected by 3 stiff lightweight rods to form a rigid object shaped like a jack. All spheres are the same distance from the connection point at the origin of the coordinate axis, and the spheres are less massive than the brass ones. So they're all going to rotate about the center there. So you're going to figure out which is going to have the biggest moment of inertia about the x-axis. So if it starts rotating about the x-axis, which is going to be the easiest to rotate, which is going to be the hardest to rotate. The shaded in ones are going to be the more massive ones. So A is going to be the least. It's going to be the easiest to turn because it has got the least amount of mass that's going to be spinning. Whereas D is going to be the hardest because it's got the most amount of mass that's spinning. And B and C will be tied because they're amount of mass is the same. Most of the time, you will be given what the equations for rotational inertia are. And you can see some of them here. For a hollow cylinder, it's mr squared. For a solid cylinder, it's 1/2 mr squared, so m being mass, r being the radius. For AP1, you will always be given that equation unless it is something that is a point mass where you need to know that it's the sum of mr squared. For APC, most of them you'll be given the equation, but some of them, like the thin rod perpendicular line through the center, this one here, and this one here, they may ask you to derive. And again, we'll get to that next week. So try another one. We have 3 flat objects below have the same mass m and the dimensions shown. The small circle at the center shows the axis of rotation, which is perpendicular to the plane of the axis of the object. So they're going to be spinning around the way you see them. So all of them have the same mass, it's just distributed differently. So you're going to rank which one of these has the most I and which one has the least, and so on. So as you can see, C has the most because the mass is furthest from that axis of rotation. A is next because the mass is concentrated on the rim. And B, it's spread out, so more of the mass is towards the center of the disk, so it's going to have the least amount of rotational inertia. A note about bike wheels. So if you have a bike, your basic standard mountain bike or whatever, then you have pretty massive wheels. And some of those snow tire bikes have really, really massive wheels. Those are going to be harder to turn because they have a higher rotational inertia. So if you're going to be in racing, you want really skinny wheels where the mass is going to be, there's going to be a lot less mass further from the center, or you want that mass distributed so that the amount of effort it takes to rotate that wheel becomes less. And then why this is important for us is because of rotational dynamics. So when we start doing our free body diagrams and writing equations again, remember that? So writing our force equations, we're also going to be writing torque equations. The sum of the torques is equal to the rotational inertia times the rotational acceleration. So it's a very similar equation to what we were using with F equals ma before.